Super lots of highlighting. I will post a video for yesterday soon. And I don't have to remind myself because it's already pre-highlighted. We're starting with the mean value theorem. The first thing is to take out 4 highlighters and highlight continuous. You don't actually have to take out 4 highlighters. But it's really important that we know that it must be continuous. And then we took out 3 different color pens and underlined differentiable. And the mean value theorem is just Rolle's theorem turned. Rolle's theorem says if you have 2 values that are exactly the same, and the function is continuous, meaning that you had to join those 2, then somewhere in between those 2 values there has to be either a maximum or minimum. In other words, somewhere there has to be a place where f prime of some point c is equal to 0, because it has to be flat. The mean value theorem says, whoa, there we go. If this is true for Rolle's theorem, it must be true if you take this shape and just turn it. Whatever the slope of these 2 blue points is, there has to be a point C that has that same slope. And the reason we start with Rolle's theorem is really obvious to, like the flat line is really obvious to see there's going to be a maximum. So it's just super intuitive. And then taking Rolle's theorem and turning it makes the mean value theorem also super intuitive. So what would you have to do here? Well, you'd have to find the slope from A to B. Do you see that this here is just your slope formula? Rise over run. Your rise is your change in your y values over your change in your x values. Then there has to exist some point C that has that same slope. Okay? So, verify that f of x equals x cubed minus 3x plus 5 satisfies the condition for the mean value theorem. Okay? So first of all, if it's a polynomial, it's continuous and differentiable everywhere. So in order to use the mean value theorem, you always have to state those 2 things to begin. So then find all the numbers C in the interval that satisfies the conclusions of the theorem. Well, the theorem says that if we find the derivative, there has to be a slope of that tangent. There's got to be a point C that slope of that tangent is equal to the slope of the secant lines that joined -1 to 1. So we need to find, if you drew this graph, you need to find the slope of the secant line, which is just your rise over your run. And here is our values. If I plug in 1 into my original equation, I get 3. If I plug in -1, I get 7. So 3 minus 7 over 1 minus -1, which is positive 2. I get a slope of -2. And my derivative is 3x squared minus 3. So at some point C, it would be 3c squared minus 3. And now I'm just trying to solve that equation. For what values of C does that work? And you have to be a little bit careful here. I'll just write careful. Both 1 over root 3 and -1 over root 3 are in -1 to 1. Can you see that sometimes you might solve and get an answer outside of the interval you're looking for? Then it's not one of your answers. We're just looking for answers in the interval. We're trying to find all the values of C within that interval that work. In this case, they both did. So now your three theorems, IVT, EVT, MVT, are easy to get mixed up. Okay? I think the extreme value theorem is the easiest to remember. It finds maximums and minimums. It finds extremes. That one's the easiest to remember. I think the second easiest one to remember is the intermediate value theorem. Because intermediate means something in between, and that's the one that says if it's continuous and you go from f of a to f of b, anything in between there has to be a value that hits that. And then the mean value theorem is the most complicated one because it's the only one that requires two things: continuous and differentiable. All three of them require continuous. Only the mean value theorem also requires that it be differentiable. And then the mean value theorem, its idea is that the slope of the secant is equal to the slope of the tangent. There's got to be a value in between where the slope of that tangent is the same as that secant. And the mean value theorem is just Rolle's theorem turned on its side. Again, Rolle's theorem says if you have exactly the same value, if your graph connected between those two values in continuous and differentiable, there's got to be somewhere where you either have a maximum or a minimum, where the slope is flat. Because of the values the same, your secant line has a slope of 0. So it's exactly the same theorem, just a really easy visual one to see. So, using the mean value theorem. So when we see mean value theorem, first of all we say, okay, continuous and differentiable. I have to state that. And this is the secant line slope has to be equal to some point on there, the tangent, the instantaneous rate of change. So instantaneous rate of change right here, that's the slope of your tangent. The average rate of change right here, that's the slope of your secant. Okay? So using the mean value theorem, first of all, we have to state continuous state those two things, that y equals sine of 3x is continuous and differentiable on 0 to pi. Since it is, we're allowed to use the mean value theorem. The slope of our tangent has to equal the slope of our secant. The slope of our tangent is the derivative. The slope of the secant is plugging in pi, plugging in 0 to see your change in y over your change in x, which happens to be 0. Because sine of 3 pi and sine of 0 are both 0. 0 minus 0, still 0. And we divide by 3. When is cos equal to 0? Cos is equal to 0 at pi over 2, 3 pi over 2, and 5 pi over 2. So inside we have 3x, so 3x would equal each of these. I have a dot, dot, dot to show that it would keep on going. How far do I need to keep on going? Well, when I divide by 3, all of my final answers need to be between 0 and pi. If I did the next one, which is, I'll do it in blue here, 7 pi over 2, and I divided that, that would give me 7 pi over 6, and that's bigger than pi. So that's why I stopped at 5 pi over 2, but I kept the dot, dot, dot to say it does. There's an infinite amount of answers. Technically, we could have the dot, dot, dot go on this side too to negative values. I didn't do that because I don't, like 0 was pretty easy to work with. I knew any negative number would cause a problem. So those are the 3 points that show the instantaneous rate of change would be equal to the average rate of change. Okay? And this idea, if we talked about rate of changes, like speed is something that is an average rate of change. Like if I traveled from here to Portage, which is, let's make math really easy, is 100 kilometers away, and it took me 1 hour, then my average speed was 100 kilometers per hour. Okay? That means somewhere along the way, I had to be going 100 kilometers per hour. It also sort of says that if I started at stop, I had to speed somewhere in order to get that average to be 100 kilometers per hour. But there must have been a moment that my speedometer said exactly 100 kilometers per hour. Okay. Somewhere along the way. It's impossible to get from here to there with an average speed of 100 kilometers per hour without some time during that my speedometer is showing that exactly. Does that make sense? And again, a lot of these 3-letter theorems make a lot of sense. But we can use them in certain situations to solve complicated questions. So they're very important that way. Step 1. Have to state that it's continuous on and differential on 0 to 2. I often like to write like when I was doing exams, I like to write to whoever was marking my exam saying, hey, by the way, I know what I'm doing. Right? And if you make it really clear like this, sometimes you might feel like, by the way, I don't know what I'm doing. Sometimes you guys write that to me on tests as well. But you do want to give that impression that you know what you're doing and as clear as possible. So first of all, it's continuous and differentiable, so we can use the mean value theorem. And we want to make the slope of our tangent equal to a slope of our secant. Our tangent, that derivative is just e to the x. And then we plug in natural log of 2 and plug in 0 and solve. Mental math. You remember the tricks for doing these? What's that equal to? I like how that came off my tongue. What is that equal to? 2. right? Because e and natural logs are inverses. So when you, like, e to the natural log, and whatever you put in here, that's what it's equal to. Because they're inverses, they cancel each other out. So this will be 2 minus 1 on the top, and natural log of 2 on the bottom. Now we just need to solve for this. How do we solve for x in a natural log? Take the natural log of both sides. Nice function here, natural log of 1 over natural log of 2. You get approximately 0.367. AP style of question, they love to give table of values. You know certain things, you don't know other things. And I think one of the reasons they like to do this is because if you got to a point where you were using calculus in a real life situation, you would probably be collecting data from something. And when you collect data from something, you don't get the function. We do a lot of work with functions to get good at it, but in real life, you get data. And then what does the data tell us? Okay? First, oh, that is a little highlighter. That's all right. And I can highlight in multiple colors. Maybe all that purple highlighters. There was a theorem that we had, obviously before Christmas, that said differentiable implies continuous. Continuous does not imply differentiable. I can have a sharp corner, but if something is differentiable, it implies continuous. So this part here says continuous, maybe even differentiable implies continuous, so it's continuous and differentiable. Therefore, we can use the MVT. Technically, we could use the IVT and the EVT as well. Because what do we need for those ones? Just continuous. We can use any one of them, but we need to state that first. Okay. So the fact that they told us it's a differentiable function from -5 to 5, maybe I even write that here on -5 to 5. You wouldn't be allowed to use the mean value theorem after that because we don't know after 5 or before -5. But our table doesn't go past it anyways. The table below gives the value of f of x and its derivative at several points. At what point does the line tangent to the graph of f of x and parallel to the segment intersect the x-axis? So it's dealing with the slope of the secant line and the slope of the tangent. So the parallel to the segment between the endpoints, that's your secant line. And if the tangent is equal to that, we need to find out where that is. So what is our slope of our secant? We just do f of 5 minus f of -5. 5 minus 45, and the distance from -5 to 5 is 10. So we know the slope of the secant is -4. Does that ever happen on our graph? Yes. right there. We need that instantaneous rate of change to be the same, and it happens at x equals -4. So we know the point is at -4, 25. But that's just a point on your tangent graph. Is that what the question is asking? The question is asking, where does it intersect the x-axis? What do we need to do that? We need the equation of our tangent line. What are the things you need for an equation of a line? You need a point, and you need a slope. We have the point. Do you see that you have the slope already as well? So we can go y minus 25 equals -4x plus 4. We want to solve when the y coordinate is 0, right? Because the x-intercept happens when y is equal to 0. So do you see what this question did as far as upping the challenge? It embedded the mean value theorem, but without an equation. And then you still had to think about, what am I finding? I need my equation of my tangent line, find out where that crosses the x-axis after that. So even in these equations that say, use the mean value theorem, okay? Make a statement that says you assume that it's continuous and differentiable. Whereas what would driving a car feel like if it wasn't continuous or differentiable? I feel like running into signposts would probably do that kind of stuff. Like power poles, boom, stop, instantaneous stopping. That would be bad. So we're going to assume that it is nice and smooth. You don't immediately go into reverse at any time and change directions instantaneously. So, what do we need? The car travels 300 kilometers in 3 hours. It must have reached a speed of 100 kilometers. I talked about this in my portage example. Okay, my average velocity is 100 kilometers per hour. So the mean value theorem says that there has to be at least one time where the instantaneous velocity was equal to the average velocity. So the car has to reach a speed of 100 kilometers at least once. Now, if you assume you start from a stopped vehicle and when you reach your destination, you would stop again, does it make sense that it would have to hit 100 at least twice? But if you didn't stop at your destination, you just flew through it, I guess technically you could just keep accelerating until you got there. But it has to happen at least once. I'm going to